Howdy, this is ESET 462 demo. What's your name?
My name is Diego Infantini.
I'm Anthony Fan.
And I'm Ryan Smeltzer. And we wanted to create our product, the Aggie with Smart Brim, because we all know the common struggle of having your baseball hat on at a football game, right? You're at Kyle Field. You want the camera to be on you, showing off your Aggie pride. However, the sun is over here because we have a freaking 11 a.m. game. Look at the sun. It's hurting my neck because I didn't bring sunscreen because I'm a real ag. But camera's on me. I'm on the screen. Where's my Aggie logo? No good. So how do you have a hat with an Aggie logo here that can protect you from the sun all the way around? And don't say sun hat because that's lame. The real answer is our product right here. Aggie with Smart Brim. So you have this main part of your hat, the Aggie. You wear this so that the logo is always showing towards the front. That's the best way to wear a hat. The thing is, the brim is on a continuous rotation servo motor and can spin around 360 degrees forever. There's no slip joints here. It's not a regular servo. We have infinite rotation. The way it tracks the light source is by using these two photoresistors. So it will detect if the light's on the right or the left of the hat. The most important detail of the hat, however, is this fin right here, because not all light sources are pinpoint. Like they're sometimes long, like these fluorescent lights up here, and you want the hat to be centered on it. The fin provides that because it won't allow the photoresistors, which have like a cone field of view, to see each other's lights. So it would always be centered, right where it's supposed to be. So, we turn it on, and Diego will go over the other electronics.
So from those photoresistors, we can adjust the response rate from them by matching equal resistors. To do that, we have two potentiometers tuned together, which cause this response to be similar to the light level as Ryan turns around here. From there, we have the battery controlling the power of the system going to the Arduino as well as the photoresistors, going down into a voltage regulator to have the proper voltage for both the Arduino, the servo motor, and the photoresistors.
Put your light on it.
From there, we have some pinouts for the servo motor that give it a PWM signal, power, and grounds. That leaves us with mostly software side, where we can then control the servo motor off of the signal from the photoresistors. And Anthony can explain that very well.
So we have the servo pins and the photoresistors connected here. Then since we have a continuous servo motor, the stop speed is 90, and to go left and right, we just make the speed go up and down, and we run into the motor. For our PID, after a lot of testing, these are the KP, KI, KD values that we used. And then I used the PID library, PID v1. It's readily available on Arduino. This serial is just for debugging when I have it attached to the computer. Obviously, we don't need it attached to the computer for it to work. We attach the servo pin, a lot of basic setup. Output max, output min is just saying how fast the left and right can really go. And send out a PID to get the result bounds. And for the loop, we read the photoresistor on the left, the photoresistor on the right. The error is the difference between right and left. These 4 lines are for debugging for myself. If the difference exceeds tolerance, and it's tolerance so it's not too finicky, I input that difference into the PID, and then with that output, I write it to the servo, and then there you go. That's the software.